Hi everyone, Mrs. Hanson here once again. Today we start a new chapter in organic chemistry, Chapter 6, looking at chemical reactivity and mechanisms. I must say the topics that we are exploring in this chapter have quite a bit of review from Gen Chem 2, and I'll just put that out there knowing how long ago that was for you. I'm unsure. It's probably different for each of us. But we will go through a little bit of review on topics such as enthalpy, entropy, Gibbs free energy, thermodynamics, and kinetics. So all of those review topics that really talk about why a chemical change occurs. What are the driving forces behind chemical change? Understanding the fundamentals of why a reaction happens allows us to begin making predictions if and true our selected reagent will drive a chemical change that we are hoping for in a mechanism. So fundamentals from Gen Chem 2 include enthalpy, entropy, and Gibbs free energy, all related to thermodynamics. So all of those topics are thermotopics. We'll do a brief review also of kinetics, how fast a reaction takes, and look at some new topics, what I would say in terms of organic chemistry, new in terms of helping us really lay a strong foundation for the reactions that are heading our way, starting chapter 7, 8, 9, all of these reactions and their mechanisms. If we just have a basic fundamental knowledge going into these, it makes it so much easier as you start drawing electron push arrows and so forth. We'll introduce nucleophiles and electrophiles, carbocations, and really focus on very specific reaction mechanisms, those mechanisms that will be used throughout the entire rest of your organic journey as you learn to predict not only what the outcome is of a reaction, but why we can predict it in such a way. So we'll explore some of these key features of chemical reactions. What causes a reaction to occur? What are those factors that affect how fast a reaction occurs? How do we represent reactions using energy diagrams? How do we draw and interpret those individual steps, each individual mechanism on an energy diagram? All of these skills we're saying are critical for understanding chemical reactivity. And here is just a shared list of your learning goals published in e-learning as well. So all of this I would say, I'm going to say even up to about here is Gen Chem 2 review. And I would say this is going to be a preview of mechanisms and important new information to lay a strong foundation as you continue, especially in chapter 7. That one is a doozy. I'm telling you ahead of time. It's our first time learning about very specific reaction pathways. So let's begin. Our first section reminds us of the term enthalpy. Enthalpy is delta H, the heat of a reaction. We understand that heat is exchanged between a reaction and its surroundings. The fundamental law of thermodynamics, we understand heat cannot be, or energy in general, cannot be created nor destroyed, but it is allowed to change forms. And in chemistry, there's a heat exchange between the system and the surroundings every time a bond breaks and new bonds form. And isn't that truly the heart of chemistry, is bonds breaking in the reactant side and forming new bonds to create products? When we break a bond, it requires energy, so it's a positive input of energy to break bonds. Breaking bonds occurs one of two ways. In a homolytic bond cleavage, think of this shared pair of electrons. In a homolytic, each one of these electrons goes in its own separate way. I want to emphasize that when we get this far, which really is radical chemistry in chapter 10, we use a different sort of arrow called a fishhook arrow. And notice that instead of having two ends on the arrowhead, a fishhook arrow only shows one side of the arrow. And it's very important because one electron is being pulled in each direction. A homolytic, I'm cleaving that bond and having the electron go one in each direction. The opposite would be a heterolytic bond cleavage. So again, here's the shared pair, but both electrons go in the same direction, and that's why we see the arrowhead completed. A heterolytic bond cleavage results in ions, where the loss of electron results in a cation, and the gaining of electrons results in an anion. So charged particles. These radicals that form from a homolytic bond cleavage are not charged. They carry no positive or negative. Radicals have an odd number of electrons, but they are not charged species. So more about that in Chapter 10 on radicals and their mechanisms. But right now we're understanding that in terms of what drives a chemical change, breaking bonds requires energy. And we have published tables that tell us how much energy is needed to break each type of bond. For example, to break a hydrogen bond in a homolytic bond cleavage, it would require 435 kilojoules for every mole. A hydrogen to carbon from a methyl group, hydrogen to carbon in an is changing slightly. So if you think about what this is methane, CH4, right? So breaking one carbon to hydrogen bond in a methane, here we have 435 kJs per mole. Here, this is an ethane molecule, and the bond distribution is slightly different because the hydrogens, I know they're a nonpolar bond, but they are next to a more electron-rich region between two carbons. So in an ethane, we have a 410. Here's the list of halogens, H to F, HCl, HBr, HI. Here's a water molecule breaking an HOH. Some other examples, breaking carbon bonds, carbon to carbon bonds. You can see ethane, propane, butane. Here we have methyl bromide, methyl iodide, methanol. Here's that OL for the alcohol. And here's a list of just halogens, the diatomic molecule of fluorine and chlorine. The complete list is given to you in your textbook on page, well, in chapter 6.1, depending on if you have an ebook or a hard copy. So just kind of letting you know that those published tables are available to you as you work to solve some problems related to bond dissociation energy. You will need access to that published table. And I put a link in there for your e-learning as well. So remember our enthalpy, delta H, enthalpy, the heat of a reaction. And I remember learning in Gen Chem 2 that an exothermic reaction is heat releasing. So the products would be more stable than the reactants. In an energy diagram, the reactants are of higher energy than the products, exothermic, heat releasing. And we would actually have a negative kilojoules of energy. For endothermic, it's climbing a hill. The reactants are of lower energy than the product. This is an endothermic reaction. So this would have a net positive sign for the heat of reaction. And so those energy diagrams that share the exo and endothermic trends are looking at the following values. I compare the starting materials, we call reactants, to the final ending products. The change in the heat content, which enthalpy here is on the Y, if the reactants release heat, we have an exothermic value. If the starting materials have to end at a higher value, we call that an endothermic, and of course it has a positive value. So we're just looking at considering endo versus exothermic and their energy diagrams. Knowing that exothermic tends to be a more spontaneous reaction, we do know that enthalpy is not the only consideration in determining spontaneity. So enthalpy, related to an energy diagram, is often used to describe the kinetics and the thermodynamics of a chemical reaction. And let's just take a look at what some example problems might look like in this section. Here I'm giving a reactant turning to products. I have a carbon in the center leading up to 3 other carbons, and therefore the fourth bond, which is not drawn but we know is there, is a hydrogen. I also have a molecular chlorine in terms of my reactants. So just kind of visually seeing what all the attachments are, and I know that these are CH3s going around here. On the product side, I still have that carbon It's leading out to a methyl, leading out to a methyl, leading out to another methyl, but now I see that it has a Cl attached to it, and the other product is a hydrogen chloride. So we're being asked to find the heat of the reaction, the delta H of the reaction. Is this an endothermic or an exothermic process? And to calculate this, you might find the easiest formula to use is to take the sum of all the bonds that are broken and subtract the sum of, that's a funny sigma, the bonds formed. And when I take the sum of bonds broken, which are on the left side, reactants break bonds, and I subtract the sum of all the new bonds that formed from the product side, we'll find the delta H of the entire equation. So as we examine what's broken and what's formed, I can see that a carbon to hydrogen bond is broken, and I can see that chlorine to chlorine bond is broken. On the opposite side, I have a C-Cl bond that formed and a new H-Cl bond as well. What stayed the same are all of these methyl groups attached to that original carbon. Those did not break. So we'll just leave them out of our calculation. So in terms of a carbon to hydrogen bond, and notice that it's attached to that methyl group there, that was given a value of 381. We also broke a chlorine to chlorine bond, which was given a value of 243. So that's a total value of 624 kilojoules of the bonds that were broken. Over here, I'm seeing that we had a carbon to chlorine bond form to right here, 331. And an HCl, and that's 431. And so that total value was 762. So when I think about products forming those new bonds and the reactants were breaking those bonds, we just simply take the sum of the reactants that broke their bonds and we subtract the products which formed new bonds, and we'll find our delta H of reaction. And if you need a little calculator for that, that's fine. On your quiz, it will be an on-screen calculator. Just pull up the tools and you'll see one appear for you. And this I found is negative 138 kilojoules. So that's really what you'll find in terms of your skill builders in this particular section, is trying to recognize what bonds broke, what bonds formed, and from there go through and find the heat of reaction. The delta H of reaction is found by taking all of the bonds that were broken on the reactant side and subtracting out the sum of all the new bonds that formed. And remember, this is the reactant side, and this is always the product side. Why don't you pause the video and try this one? Come back when you'd like to check to see if we get the same answer. All right, so here's a carbon attached to an iodine and attached to 3 other carbon. So make sure when you're using your bond dissociation chart, you're actually finding the correct CH, the carbon leading out to 3 other carbons and attached to the iodine. So right here is the value of 209. So I can see that we're breaking a carbon to iodine bond, and that costs the molecule 209 kilojoules of energy. The next reactant I see is water, and what we're breaking there is an HO bond in the water, and that costs the molecule 498 kilojoules of energy. So we'll take this sum and subtract over on this side what's being formed. So again, here I have a carbon attached to 3 other carbon, now as an alcohol functional group, a COH. And again, I went to the chart, my bond dissociation energy chart, and found 381 Don't wait for test day to make sure you can find these values. Please become familiar with the table of bond dissociation energies. And I can also see a new bond forming between H and I, and I can see that is a value of 297. So the sum of broken minus formed, and I'll take my 209 and add 498. Its sum of 707. 381 when added to 297. Well, that's not right. Not it again. 381 plus 297 gives us a value of 678. 707 minus 678. And this came out to be a positive 29 kilojoules, which would show us that this is an endothermic positive. So that graph would have a feel of reactants forming products that are of higher energy, endothermic. And really that's it about in terms of calculating enthalpy. You'll just use a bond dissociation chart and be asked to find if it's endo or exothermic, and be familiar with how to use that table of bond dissociation energies. Well, in thermodynamics, we know that there is a second consideration to determine if a reaction is spontaneous. Enthalpy, delta H, is just one of those, the heat of a reaction. Entropy is a second thermodynamic property. We think of entropy as the measure of a disorder associated with the system. The more microstates that are possible, the higher the entropy of the system. So think of entropy really as describing the probabilities of a system. The more chaotic a system, the higher the entropy. And a spontaneous reaction favors positive entropy. We want the system to become more chaotic as a driving force for a chemical reaction. So entropy is the second thermodynamic property to consider in addition to the enthalpy unit delta H. Remember that entropy is just chaos, molecular disorder, randomness, freedom to move. So for instance, gases have higher entropy than liquids. Liquids have higher entropy than solids because the freedom to move in space increases with those solid, then to liquid, then to gaseous phases. So it's really vibrational, rotational, translational states of energies as a compound is distributed. The more chaotic, the higher the entropy. And think about why a gas is actually allowed to expand and diffuse into any empty space. So if I have a closed vessel, these gas particles will randomly disperse inside the container, and if I open the valve, it will increase its entropy, which is favorable, by moving to a larger volume. So more volume creates more microstates, which means that it has greater entropy. The entropy of a system plus the entropy of the surroundings gives us the total entropy of the universe. Really, this is what I always called the universe, and you're talking about the laws of thermodynamics. So to be positive, which is favorable, we need a positive entropy, and that considers both the system and the surroundings. For us, the system is typically the reactants, and the surroundings typically are the solvent. So let's talk about things that affect entropy. Remember, the random chaotic factors. So the system, we said, we're recognizing as the chemical reaction. An increase in entropy would occur if I take a single compound, like a compound AB, where A is chemically bonded to B, and I break those apart, where 1 mole turns into 2 moles. This would be classified as a decomposition reaction. That's a favorable entropy. Entropy has increased, and that's a favorable term. Another way to increase entropy is to take a cyclic compound and break a bond. Take a cyclic compound and break a bond, and this is a more disordered arrangement as compared to a cyclic compound, which would be more ordered. So breaking cyclic structures increases entropy as well. Going from solids to liquids, liquids to gases are also ways to increase entropy. And this is just a practice opportunity from your skill builders in your text. Will the delta S, the entropy of the system, be positive or negative? If it's positive, we know it's becoming more chaotic, which is favorable. And if it's negative, it's becoming more ordered, which is not favorable for spontaneity of a reaction. Here I have an equation in letter A where I have one reactant combining with a second reactant to produce a single compound. This we would recognize as a pattern of change called a combination, because we're taking two compounds and forming one. This would be a more ordered state, so this would be a negative entropy, which means it's more ordered. Now here in letter B, I'm taking a structure and closing that to create a cyclic structure. So an acyclic turning into a cyclic structure is actually a more ordered system, so that's negative entropy. Here I have a compound in letter C that is breaking apart into two separate ingredients. We call this a decomposition pattern, where compound AB is breaking into two separate compounds. So here we have 1 mole forming 2 moles, which is a more chaotic, more microstates. So this indeed represents a positive entropy, more disorder, more microstates. Sorry. Here in the next example, letter D, I have a single compound breaking apart into 2 separate pieces. 1 mole converting into 2 moles creates a positive entropy, which is favorable. Notice here I still have A plus B forming AB. This is also a reactant. Even though it's just sitting on the arrow, it's still part of the reaction. So this is becoming more ordered, so this is a negative entropy. And then finally, looks like here, we just take a cyclic compound and turned it into an acyclic compound, which tells me that's more disorganized, so that's a positive entropy. All right. Putting those thermodynamic properties together, we form Gibbs free energy, that classic thermodynamic equation that allows us to determine if a reaction will be spontaneous. Remember that the totals, and I always called this the universe, the total amount of entropy in the universe is the sum of the system and the surroundings. If you just simply rearrange this equation to isolate the system and the surroundings, isolate that to have delta S surroundings, and we have this equation where it's equal to negative enthalpy of the system over the temperature, and that has to be in the Kelvin units. And we come up with what we're leading into is the Gibbs free energy equation. And I'm not asking you to memorize the workup to it, but you will have to understand the Gibbs free energy equation to predict if a reaction will be spontaneous. So as we rearrange the enthalpy term and the entropy term, we define Gibbs free energy. And again, this was worked up for you in your Gen Chem 2 series. It's defined as negative T delta S total. Well, all right, Gibbs free energy, it's just a measure if the reaction will be spontaneous or non-spontaneous. We must have a negative value of your Gibbs free energy for the reaction to occur in the forward direction. Negative delta G means the reaction is spontaneous in the forward direction. If I have a positive delta G, the reaction is spontaneous in the reverse direction. And if you have 0 equal to the delta G, the reaction is at equilibrium. Alrighty, so that's kind of what we're asking you to determine, and just saying if a reaction occurs, there needs to be a driving force. The two driving forces work together, enthalpy and entropy. And the delta H minus T delta S relationship allows us to see if our equation is valid. Are we trying to drive a reaction forward? Well, we better have a negative delta G. Are we trying to drive a reaction in the reverse? Well, we better have a positive delta G. And those are our considerations when we start to propose mechanisms to drive chemical change. Now, I just want to make a note. Typically, delta H is always given to us in kilojoules, and delta S is usually given to us in joules. Make sure you convert if you're asked to calculate. Make conversion, all right, into one like unit. Now what I would do is put joules to kilojoules so that your numbers aren't so large. If we think about a reaction, and we've been stressing that there's two thermodynamic properties to consider, enthalpy and entropy, we understand that this reaction has an unfavorable entropy. This is becoming more ordered, so that's a negative entropy. However, the reaction does occur. It is a spontaneous reaction. And so what does that mean to us? If I know delta G has to be negative, and it is negative because they're telling us this reaction occurs, and I know that the entropy is negative. Remember, it's negative of a negative, which is really the same as saying positive. That looks like a person, doesn't it? The negative sign for the temperature, negative delta T, and if this is indeed a negative value for S, we end up to have a positive sign in there. That means that this must be very, very exothermic, which is a negative number. This number has to be so largely negative that even if I add a little positive sign onto it, it still remains negative overall. So what we're saying is enthalpy can still be large enough to overcome an unfavorable entropy. And I know that you spent time in Gen Chem 2 with some similar chart where you had to consider all the possibilities to have delta G as negative, positive, or it could go either way, right? So if delta G is equal to delta H minus T delta S, how do I get this to be negative? Well, if my reaction is exothermic and the process is becoming more chaotic, this will always be a negative process, always spontaneous. Boy, that is always what we would like. Exothermic with an increase in disorderness, that'll be a spontaneous reaction. However, what if we have an endothermic, but the system is becoming more chaotic? So that is a favorable entropy. What type of temperatures would we need to promote a high value to get delta G to be negative? We got to have a really high temperature. This number has to be very large so that I can overcome an endothermic process. If we have exothermic and it's becoming more ordered, which is an unfavorable process, we need to run this at very low temperatures so that this value doesn't overcome the delta H is negative. So low temperatures there. And if you have an endothermic process and your system is becoming more ordered, you will never get that reaction to proceed. Spend time with those conditions so that you can predict if a mechanism, if the proposed mechanism for a reaction that you'd like to see occur, does it have the correct driving force? And so when we think about these energy diagrams for Gibbs free energy, notice that it's delta G now on the y-axis. A moment ago we had delta H for enthalpy. This now places delta G, so the vocabulary word is just a little different. It's exergonic if it is a favorable negative delta G. This reaction is a spontaneous reaction with a negative delta G. That is an exergonic reaction. And the opposite of that would be an endergonic reaction, where we have a positive delta G. And so in the forward direction, this would be a non-spontaneous reaction. So let's kind of talk through a little bit about, what would create a spontaneous reaction in the forward direction. We need a negative delta G. If we had a positive delta G, think of that as being spontaneous, but in the reverse direction. And if we're at equilibrium, we actually have 0 as the delta G value. Alrighty, so let's consider a little bit more about equilibrium. And I know you spent a great deal of time on equilibrium in Gen Chem 2, at least 3 chapters worth. So let's consider a negative delta G, which means the products are being favored. All right, so the equilibrium will eventually be reached with the greater magnitude of negative delta G, the greater the concentration of products. So again, if I see that if I had a reaction coordinate where I started like significantly different, if this were of higher energy, this value determines, this value here is significantly different as compared to here. So this would favor the products even more, because it's a favorable change of lower energy. Systems want to lower their energy. So that magnitude of delta G tells us even how far we lie to the right of our equilibrium. So we have an exergonic process, but yet it does not yield. Typically, you won't get 100% of the reactants to convert to the products at any one time, because a system lies with equilibrium. What that means is if we consider A plus B in dynamic equilibrium with C plus D. So that means we have a forward and a reverse reaction occurring. Think about just the collision theory. When the reaction proceeds, when it first initiates, A collides with B. And as A collides with B, the reactants are getting consumed. Reactants get used. And as time goes by, products begin to get made. And so now all of a sudden, we have a competing process. The collisions between C and D begin to occur, and those collisions are going to force the reverse reaction to occur until you reach dynamic equilibrium, in which the forward rate is equal to the reverse rate, and it's at the minimum amount of energy. A and B are colliding to produce C and D at the same rate that C and D are colliding, going back to A plus B. A dynamic equilibrium when the forward and the reverse rate are the same. We understand equilibrium is just an expression of the concentrations of the products over the concentrations of the reactants. And we used this equation to relate Gibbs free energy and the natural log of the equilibrium constant. Equilibrium constants, Gibbs free energy, enthalpy, entropy, these are all thermodynamic terms. They really just describe the relative stability of the products and the reactants. What it does not tell us anything about is how long it takes for the reactants to convert to products. There's no kinetics information. Remember that when you're calculating here, we have to use 8.31 as the gas constant. T has to be in the Kelvin scale. These will come out in kilojoules of energy. This has no units. Alrighty. Notice here that we're just looking at values of kilojoules for Gibbs free energy. The more negative the Gibbs free energy is, the more we favor the products in terms of lying to the right. So I would think of A plus B is in equilibrium with C plus D. If there's a significant difference between energy, and this would be something like, very significant, then that's going to really favor the product side. By the time you're down at a Gibbs free energy of 0, let's kind of look at what that would look like. We'd have a little energy barrier, but you would start and end at the same space, the same amount of kilojoules, so that the difference between reactants and products is 0. Your equilibrium is 1. That means you have an equal amount of reactants and products. And remember, these are non-spontaneous, but positive values. And so you're looking at values like this for Gibbs free energy. The more positive, the more you're lying to the left of the equilibrium, which would be spontaneous in the reverse direction. Alrighty. So let's kind of think through some examples. Maybe you want to pause, read through these examples, and come up with a thought. How would you answer the following questions, giving you some process time? Pause the video and really think about these questions. Don't cheat yourself of the thought time. Come back when you're ready to discuss them. Okay, so I'm welcoming you back. I hope you gave yourself some think time. Turn me off sometimes and just let yourself think. We're being asked if the reaction favors the left side or the right side, the reactants or the products. In letter A, I notice that I'm given a positive sign on the delta G. A positive sign for delta G indicates that the reaction is spontaneous, but in the reverse direction. Letter B, a reaction for which the equilibrium constant is 0.5. That's a pretty tiny number, isn't it? So if it's smaller than 1, think about the ratio of products over reactants. And we come up with a 0.5 value. Remember, the larger and larger and larger the number is, favors the products. And the smaller and smaller and smaller the number favors the reactants. So this is a small number, so I'm going to say it favors the reactants. Now I know that K's can have a value of like 1.8 times 10 to the negative 6. That's the Ka for acetic acid. Just know that one. And that's a really tiny number, so I can clearly see that's favoring the left side. But KEQs can have magnitudes of like 10 to the 9th power, which is an extraordinarily large number, which would very much favor the right side, the products. Here we have a reaction carried out at 298 Kelvin. The delta H is given as positive, and the delta S is given as positive. So this is an endothermic process. This is becoming more chaotic, which is good. We have a positive entropy, and the temperature is 25 Celsius, which is typically room temperature where you're running your lab at. We want to know the sign on delta G. Now, to be safe, you can actually calculate and determine the sign on delta G. We have 33 kilojoules per mole as your delta H. In a parenthesis, it's negative T delta S. So this is 273. I want you to just make sure you're seeing that equation. If I do positive negative T delta S, I'm just rewriting that as negative T delta S. And then the delta S, but remember this is joules, so 150 joules. Oh, I'm going to just remind you that we have to put 150 joules over 1,000 to get it to be a kJ, and then we could have like units. Alrighty, so I'm going to just hit for us 0.15. That's 0.15 kilojoules for the delta S. And then times 273. And that's going to be 40.95. 33 minus 40.95. And see what we've done? We've simplified that equation to find delta G came out as negative 7.95. So this again would be spontaneous in the forward direction, and so it's going to favor products. Using this chart we just kind of went through in terms of, we had an endothermic reaction, but it did become more chaotic. We need a high enough temperature to overcome the endothermic process, and that indeed happened there. If an exothermic reaction has a positive value for the delta S of the system. Now, as you think about that, the system we had to define, so delta H of the products, delta S means that delta G is always negative. And so I just want you to think about letter D. It's going to favor the product side because we have a positive entropy and we have an exothermic reaction. And then finally, the endothermic process, what a negative value, and you'll say that that's never spontaneous. And I bet for letter E, you wrote that that was also favoring the reactants. Good work. Blast from the past of Gen Chem 2. Just a little bit about kinetics as well. Recall that a negative delta G might tell us if a reaction is spontaneous in the forward direction, but it gives us no information about the rate of a chemical change. And that was a whole topic in of itself called chemical kinetics. So the spontaneity of a reaction tells us if it occurs. It's the kinetics that tell us how quickly a reaction will occur. And they give this prime example of, carbon in its graphite form will spontaneously turn into a diamond, but it just takes tens of millions of years. Even though it's a spontaneous reaction, it really doesn't occur with a meaningful rate. Those things that can affect a chemical kinetics, how fast a reaction occurs, are, number one, the concentration of the reactants. If I increase the concentration, I increase the number of collisions. More successful collisions occur, the reaction will speed on its way. The activation energy, how high is the energy barrier that separates reactants from products? The temperature, raise up the temperature, more kinetic energy, molecules move faster, more collisions, again, a faster kinetics. The geometry and sterics of your mechanism, are you have any inhibiting factors in your mechanism? And again, the presence of a catalyst that can lower the activation energy. Let's talk about each one of these briefly and remind us of what we once knew for sure about kinetics. We express kinetics by using a rate law. Rate is equal to K, which is called a rate law constant. And we express the reactants in terms of concentration, typically molarity units or sometimes pressure units. And that rate depends on the rate constant and the time, right? The concentration of reactants over time. And what we come up with is what's referred to as the order. The order of the reactant is how changing its concentration affects the overall rate. If you have a first order reaction, if you doubled the concentration, the rate follows in the exact same process. So if I doubled the concentration from 1 to 2 in a first order, the rate will also double. In a second order reaction, if I double the concentration, the rate will actually quadruple. So if concentration A is doubled, I wrote A. If I doubled the concentration of A in its second order, it will actually quadruple the kinetics, how quickly the reaction occurs. So second order overall, first order with respect to A, first order with respect to B, or you could have a third order reaction where you have rate is equal to K, A is to the second order, B is to the first order, third order overall. All of that just comes back to us in terms of recognizing the things that increase the rate of a reaction. Sometimes we actually want to slow a reaction down to have better control. So what are those things we can do? Maybe like cool it, right? Or take out the catalyst if we're having the reaction occur too fast. So let's just quickly highlight each one of those factors. The activation energy we know is the definition of the barrier that separates reactants from products. It's that minimum amount of energy I've got to get over before the products form. So the molecular collisions must be successful enough to overcome the activation energy. The lower the activation energy, the faster the rate. These products will occur faster than these products. So I'm getting an idea of the rate of a reaction by just looking at the energy barrier. If I raise the temperature of a reaction, again, more kinetic energy, more collisions, more successful collisions, therefore you'll have a faster kinetics. The reactions will occur faster at higher temperatures. The third factor we talked about was steric consideration. Just think in terms of the molecular geometry. As these molecules collide, they have to do so with just the correct orientation in space, just enough, oomph to have bonds actually break. So if the reactive conformation of a compound is extremely high, it just spends less time in that conformation. And so the probability of a collision resulting in that type of conformation is quite low. We studied conformational analysis in Chapter 4. We want to alleviate any steric hindrance. So don't rely on a molecule that has to have an unusual high conformational energy to lead to your product. The presence of a catalyst really just converts the pathway to involve a lower activation energy. Enzymes are examples of nature's catalyst. Catalysts lower activation energy without themselves being consumed. So they're placed in a reaction and brought back out unchanged at the end. Now, just look at the two different graphs and think about two driving forces: kinetics, how fast a reaction occurs, and thermodynamics, which is, are they favorable to occur? When I think about kinetics, I want you to focus on activation energy, right? The activation energy is related to how fast a reaction occurs. When I compare this reaction to this reaction, clearly I would faster kinetics because the activation energy is significantly smaller as compared to that exaggerated graph. The second graph you're looking at tells us about thermodynamics. Thermodynamics is the difference in energy from the reactants to the products. And so consider this type of energy difference versus this type of energy difference. Clearly you see that this would have more favored energy because it's significantly lower than where you started with. So I'm favoring the products in the thermodynamics, and I can tell rate by the amount of activation energy. So let's practice that with some graphs. Here we have two reactants, A plus B, and I see two different pathways. One's in red, one's in blue. Clearly the red has higher activation energy and therefore is not favored for kinetics, right? So what will happen is these will form faster and E and F will form slower. I can get the kinetics information out just by looking at the activation energy. Now consider what's happening in terms of the thermodynamics. I want to compare the starting amount of energy to the ending amount of energy. So E and F really didn't change too much, whereas C and D had a significant lowering of energy. So these are going to be thermodynamically favored. They're of lower energy. And this is going to be kinetically favored because it had a lower activation energy. So it's both. I'll just put that up here, kinetically favored, then it's not written over there. Kinetically favored because this activation energy was smaller than compared to the red line. Here we have an example where A and B have two different pathways. A and B in the blue pathway have a significantly higher activation energy than in the red pathway. So the red pathway would be favored kinetically. And in this blue pathway, because C and D end at a lower energy, this is going to be thermodynamically favored. As you look at your transition states and intermediates on an energy diagram, let's make sure we can fill in each of these vocabulary words. We know that reactants are the starting materials. The products are the ending materials. But I'm seeing a mechanism here that has multiple steps to get from reactants to products. At the top of each energy hill, at the top of the energy barrier called activation energy, are known as transition states. This is where bonds are breaking and new bonds are forming. You cannot isolate a transition state. You can't pull it out of your reaction vessel and measure it because it's an instant in time where bonds are breaking, new bonds are forming. Now, intermediates, these are substances that get made and then immediately used in the next step. So I'll say made as a product in one step, but immediately used as a reactant. Intermediates can be isolated. You can take them out and measure their concentrations in your reaction vessel. So intermediates lie at the bottom of these energy steps, whereas the transition states are up high on these energy steps. We have 1, 2, 3 transition states, and we have 2 intermediates in this particular energy diagram. So these transition states are at the high energy state. Notice that they're forming and breaking bonds. So here's an example of a transition state where I can use these little dashed lines to represent bonds breaking and new bonds forming. So they're fleeting, they cannot be observed, and on the energy diagram, they are just simply there to represent the top of the energy maxima. They are breaking bonds and forming new bonds along the way. These intermediates lie here on an energy diagram. They can be isolated, but see how they are made and then immediately consumed along the way. There's 2 points on an energy diagram that are close in energy, and they should be considered very similar in structure. Notice in an exothermic process, such as this diagram, the top of the energy barrier is closest to the reactants as compared to the products. These are farther away. And what we're suggesting is the closer the energy barrier is to one side or the other, reactants or products, that means that it's going to resemble the reactants or the products more. So based on this assumption, we generalize that the structure of the transition state depends upon whether the reaction is exo or endothermic. In an exothermic reaction, such as this energy diagram, your transition state resembles the reactants. And in a next diagram, when you see that your transition state for an endothermic process places the activation energy closer to the product, the transition state will closely resemble the products instead of the reactants. Exothermic transition states resemble the reactants. Endothermic, the transition states resemble the products. I'm going to encourage you to pause the video here and process this question in your own head. Please give yourself some think time and then come on back when ready. All right, are you back? Well, let's talk. Let's compare A with D. which process occurs more rapidly? Now, I want you to think about kinetics when you're talking about how rapid a reaction occurs, and that's a measure of the activation energy. So really what you're asking yourself, which process occurs more rapidly? Which has the smallest activation energy? That's really all it's asking us. In energy diagram A versus energy diagram D, D has lower activation energy, so D is going to occur faster. Let's compare A and B. Which will more greatly favor the products? And so this is a thermodynamic consideration. And what we want to know there is to favor the products, you want to have the negative delta G. The larger the delta G is negative, the difference between the starting and ending material. So here's the delta G for reaction A. And look at this guy for B is just really about the same. That's about 0, wouldn't you think? So this is a negative delta G. Certainly A is going to be favored over B. Let's compare A with C. Which case will the transition state closely resemble the reactants more than the products? And just think about the distance between the energy hill in letter A, very close to the reactants, and in letter C, very close to the products. So it is A that resembles the reactants, and in case C, it would represent closer to the products. And that's how we interpret those graphs. Not too bad. I'm going to pause our first lesson here. You've done some great review of Gen Chem. Come on back for lesson 2 and we'll pick up some new topics, kind of seeding a lot of material that's heading our way in future chapters where we start to consider specific pathways and mechanisms of reactions. Come on back when ready.